Hello everyone. Today I will present the liquid-liquid extraction (LLE). The objective of this video is to provide a comprehensive overview, core principles, and applications of the LLE process. LLE is a separation process involves the transfer of a solid from one liquid phase to another, typically from an aqueous phase to an organic phase based on differences in their solubility. Common equipment used includes separation funnels, mixer settler, and the extraction tower. For the separating funnel, based on the difference in the densities of liquid components, the higher density liquid sinks to the bottom and can then be drained from above, leaving the less dense liquid in the funnel. To provide efficient mass transfer, a mechanical mixer is often used to provide intimate contact of the two liquid phases. The feed of aqueous phase and organic phase are mixed in a mixer, and the mixed phases are then separated in a settler. One phase is usually dispersed into the other in the form of small droplets. Sufficient time of contact should be provided for the extraction to take place. Small droplets produce large interfacial areas and faster extraction. Both types of mixer settlers can be used in series for countercurrent or multiple stage extraction. In the spray extraction tower, mixing and settling proceed continuously and simultaneously. The heavy liquid enters the top of the spray tower, fills the tower as the continuous phase and flows out through the bottom. The light liquid enters through a nozzle distributor at the bottom, which disperses or sprays the droplets upward. The light liquid colors at the top and flows out. LLE is based on the partitioning of solids between two immiscible liquid phases, typically water and organic solvent. The process involves the following steps. Phase mixing. The solute is initially mixed with the two immiscible liquids. Solute partitioning. The solute moves from the more concentrated phase into the solvent phase due to differences in solubility and distribution coefficients. In separation, the two phases are then separated using techniques like gravity separation, centrifugation, or filtration. Recovery. The desired solute is extracted from the solvent phase, often requiring additional processes such as solvent evaporation or distillation. Equilateral triangular coordinates are often used to represent the equilibrium data of a three-component system since there are three axes. Each of the three corners represents a pure component A, B, or C. The point M represents a mixture of A, B, and C. The perpendicular distance from the point M to the base AB represents the mass fraction of C. The distance to base CB is the mass fraction of A, and the distance to base AC is the mass fraction of B. Since triangular diagrams have some disadvantages because of the special coordinates, a more useful method of plotting the three-component data is to use rectangular coordinates. The solvent pair B and C are partially miscible. The concentration of the component C is plotted on the vertical axis and A on the horizontal axis. The concentration of component B is obtained by difference from calculation. The two-phase region is inside the envelope and the one-phase region outside. A tie line is shown connecting the water-rich layer called the raffinate layer and the ether-rich solvent layer called the extract layer. The raffinate composition is designated by X and the extract by Y. Hence, the mass fraction of C is designated as YC in the extract layer and as XC in the raffinate layer. Applications of LLE in chemical industry. It is used extensively for purifying chemicals, such as separating valuable products from byproducts in large-scale chemical reactions. LLE also plays a key role in separating and recovering rare earth metals from ores and industrial waste. In pharmaceuticals, LLE is utilized to isolate active pharmaceutical ingredients from plant extracts or synthetic compounds. This helps in ensuring higher purity and concentration levels for further formulation and testing. It is also employed to optimize the solubility and bioavailability of certain drugs by selecting appropriate solvents that enhance the compound's absorption in the human body. In environmental monitoring and remediation, LLE is used for the removal of contaminants such as heavy metals, organic pollutants, and other toxic substances from wastewater and drinking water. This technique is useful for extracting and recovering hydrocarbons from water bodies during oil spill incidents, reducing environmental damage. In food and beverage industry, LLE is used in the extraction of essential oils from herbs, spices, and flowers for use in flavoring and perfumes. The food industry also uses LLE to isolate compounds like vitamins, antioxidants, and pigments from raw materials for functional foods and nutraceutical products. In petrochemical and energy sectors, LLE is employed in the extraction of specific hydrocarbons from crude oil, such as in the separation of aromatics and resins. In biofuel production, LLE helps in separating biodiesel from other byproducts during the refining process. The challenges in LE is the solvent recovery. The recovery and recycling of solvents used in LE can be energy intensive and costly. Solvent toxicity. Some solvents may be hazardous, requiring proper disposal methods to minimize environmental and health risks. Phase separation issues. In some cases, the separation of phases may not be efficient, requiring the use of specialized equipment or extended processing time. The future of LLE lies in overcoming current challenges through technological innovations. Some of the anticipated advancements include green solvents, development of non-toxic environmental friendly solvents that reduce the environmental footprint of LLE, microscale and continuous LLE, miniaturization of LLE processes for faster, more efficient separation, especially in laboratory scale applications and for high throughput screening. Integration with other separation methods, combining LLE with techniques such as chromatography, membrane filtration, or supercritical fluid extraction to improve separation efficiency, automation and process control, adoption of advanced process control techniques such as real-time monitoring and optimization to enhance LLE efficiency in large-scale operations. As a conclusion, LLE plays a vital role in a wide array of industries from chemical industry to petrochemical and energy. It is an essential process for purifying compounds and separating valuable substances from complex mixtures. As technology advances, new methods are emerging that promise to enhance extraction efficiency while minimizing the environmental impact.